Today we're going to talk about linear inequalities in two variables. And to start off, I sort of want to basically redo what we did yesterday, just a quick recap. So yesterday we were sketching linear functions, lines basically. So I don't know, call it a recap, call it a review. But this was an example question that I asked you to do yesterday. Say sketch y equals 2x minus 1, right? Just a quick, simple linear equation. Okay, that's a sketching problem. It's in slope-intercept form, so I don't need to solve for y. I'll go ahead and plot down a coordinate system. Draw my tick marks. And the idea is that this very last number here is your starting point. That's your y-intercept. So I'm going to put a y-intercept of -1. And then my slope is really a fraction, 2 over 1. That tells me from my starting point, I'm going to go up 2 spaces and over 1. Or I can go down 2 spaces and left 1. Either way is fine. And then the idea is you connect the dots. So I totally missed that, but you guys get the idea. Now this line consists of more than these 3 points. I only graphed 3 points just to form the physical line, but there are other points on this line. For example, I could have easily, from any of the other green points, go up 2 over 1, or maybe from this point down 2 over 1. So there are lots of different points that make up this line. Let's actually label some. So what is this? 2, 3. This is 1, 1. This is 0, -1. This is -1, -3, so on and so forth. So yesterday we were graphing lines, but you know what? I don't think we really understood what the heck we were doing. Yeah, physically we were plotting points and connecting the dots, and right now we're not listening to the lesson when we should be listening. Thank you. But I sort of want to know what's so special about this particular line to this particular equation. Well, if you consider the point, let's say 2, 3, with the equation y equals 2x minus 1. I hope everyone understands that every single coordinate is just an x and y value. It stands for two numbers that I can plug in to the equation. So if I plug in x equals 2 and y equals 3 into this equation, we get 3 equals 2 parentheses 2 minus 1. We get 3 equals 3. Well, if I consider another point, just a random point, let's say 1, 1. That's another one that we listed with the equation y equals 2x minus 1. So we get x is 1, y is 1. 1 equals 2, parentheses 1 minus 1, and we simplify to 1 equals 1, which is a true statement. And just for fun, let's do one more. Let's do -1 and -3. That was another point that we listed. So if we consider -1 with -3 with the equation y equals 2x minus 1, again, the x is -1, the y is -3. So we get -3 equals 2, -1 minus 1. We get -3 equals -3. So these 3 points that I just picked randomly from the line, when I plugged it into the equation, it gave me a true statement. Would you agree that that's what we call an answer? That's what we call a solution. Because when I plugged this point into this equation, it gave me a true statement, I would say the point -1, -3 is a solution. And all of this is true for every single point on this line. And that's sort of the idea there, that a line consists, or what a line contains, is a whole bunch of answers, a whole bunch of solutions. A whole bunch of solutions for a particular equation, the equation that you're graphing. And that's sort of the algebra interpretation of graphs. We already have a geometry interpretation of graphs. Yeah, a graph is just the shape of an equation. But this is the idea, or the algebraic idea, of a graph. An equations graph is a visual representation of the equation's solution set. And that is a technical term, solution set. So if you don't know what solution set is, a solution set is a collection of all answers. So that's what a graph is. When we look at a graph, when we look at a line in this particular instance, we're actually seeing every single answer to that equation, every single x and y that makes that sentence true. Which is why when we graph a line, it is very, very precise. It follows a nice, neat pattern. I'm just going to draw a random graph here, no numbers, just a random graph. So here's a coordinate system. Here's a random line. And let's say that line has an equation y equals f of x, right? Just some arbitrary function. Again, just to reiterate, every single point in that line is a solution to the equation. So that point is a solution, this point is a solution, this point is a solution, that point is a solution, and that point is a solution. It is very, very strict. If you somehow are just off by a smidgen, by a centimeter, say, like right there, super duper close, right? It's super duper close, but technically it's not on the line. This is not a solution. Equations are very strict. It has to be precise. If the answer is 2 and you give me 2.0000000000001, sorry, for an equation, that's not the right answer. It has to be precise. Now, why am I harping on this? Well, because when we graph equations, because they're so precise, all of your answers will always lie on the shape itself. This lesson is all about inequalities. So, since inequalities allow for, and I'm going to use a mathematical technical term here, some wiggle room, solutions to linear inequalities may be off the line. Right? And so that's the only thing that differs between today's lessons and yesterday's lesson. Yesterday's lesson we were graphing linear equations, so your solution set, the answer, was that precise line, no more, no less. But today, since we're talking about inequalities, because inequalities are flexible, it gives you lots of options, your answers may be off the line. Now, if we're talking specifically about linear inequalities, our solution sets will be half planes. Right. And that is a technical term. It literally means what it sounds like. Your answer to a linear inequality will always be half of your coordinate grid. Right. Some quick examples here. Bless you. So this line here would be an answer to a linear equation, but if it was inequality, my answer could be every single point on this side of the graph. Or it could be, oops, I didn't want that. It could be every single solution on this side of the graph. So the answers are more than just a line. The answers are literally half of the picture. So here are questions. Okay, Mr. Vo, how do I know what half it is? Mr. Vo, how do I graph the various inequalities? Because inequality symbols, there are more than just one. Here are some things to consider, to keep in mind when you're sketching linear inequalities. Things to consider. We typically separate inequalities into two categories: the exclusive inequalities and the inclusive inequalities. If your inequalities are exclusive, that is to say, it is strictly less than or strictly greater than, when you graph your line, these will be dotted or dashed, however you want to do it. That will indicate that the boundary line, that the physical line that we're drawing, those points are not part of the solution set. Conversely, if your inequality is inclusive, that is to say it has the or equals to part, these would be solid lines. Where to shade will be dependent on the inequality. And my technique or my advice to figure out how to shade or where to shade, just read the inequality and in my abbreviation, WRT is with respect to. Read the inequality with respect to the y variable. Let's take a look at an example to see what the heck I mean by that. So for example, if I ask you to graph, I don't know, y is strictly greater than 1/2 x minus 2, say, I don't know, just making it up. Okay, you just run through the motions of yesterday. I can do this. I'm going to graph my coordinate system. It's already in slope-intercept form, so I am happy there. I'm going to draw my tick marks. Same motions as yesterday. My starting point is a -2, so I'm going to draw a point there. My slope is 1/2, so I'm going to go up 1 over 2, or I can go down 1 and left 2. And if this was yesterday's lesson, I would just go ahead and connect the dots. However, because my inequality is an exclusive, that is to say, it is strictly greater than, I have to draw a dashed line. So just go ahead and draw a dashed line. Now, this is the question I always get. Okay, so Mr. Vo, do I shade to the top? Do I shade in the bottom, left, right, so on and so forth? What you have to do is you have to read the inequality. What does this say? This says y is greater. All I did was translate. That literally says y is greater. Now, we should know on a coordinate system, here's x plus, here's y plus, x minus, y minus. Okay. The inequality says you need to graph the y values getting bigger. On a regular coordinate system, which direction, right, left, top, bottom, which direction do the y's get bigger? Up, right? So that tells me my solution set, if I pick any random point on my dotted line, my solution set needs to go up. Any point I pick, my solution set needs to go up. So that tells me my answer is this dotted line with this shading here. That is the proper shading for that inequality. I didn't have to memorize it. I know a lot of teachers go, wait, if the arrow is pointing to the left, you do this. Don't memorize those rules. It's just read it and then shade whatever it tells you to shade. Because it says y has to be bigger, I'm going to shade all my y values getting bigger. Okie dokie? Let's do, I have 2 more examples prepared. We can do 3 more if we need to. Let's do this example here. Let's say 5x minus 2y is greater than or equal to -4. Oh no, it's in standard form. Well, what did we do yesterday when we had problems in standard form? Change it to slope-intercept form. Just solve it for y. That's it. So if I give you a problem in standard form, don't freak out. Just solve for y. So to solve for y, I'm going to subtract the 5x. We have -2y is greater than or equal to, I like to write the x first, so I'll write the minus 5x first and then minus 4 second. And then the last step is to divide up the -2. Only reason why I wanted to do this example with you guys is most kids forget when you multiply divided by negative, you must flip the inequality. Now that's in slope-intercept form, you can go ahead and graph this. So I'll go ahead and draw my coordinate system. Draw my tick marks. My y-intercept is a +2, so I started at a +2, and my slope is 5/2. So you go up 5 over 2, or you go down 5, left 2. Oh yeah, because over here we had a negative divided by a negative is a positive. And then since the inequality is or equals to, it's going to be a solid line. If this was an equation, that would be my answer, but since it's an inequality, I have to do some shading. If I read the inequality, it literally says y is less than. Which direction do y's get smaller? On the bottom, that means for every single point, my solution set should go down, which means this is the correct shading. So knowing how to shade is just a matter of being able to read the math symbols. Okie dokie? Yes. Last example I have, unless you want me to do more, is these ideas work even if you had special lines. Say, for example, x is greater than -2. I know that this is a special line because it only has one variable. If I'm asking you to graph lines and I only give you one variable, you know it's going to be special. The special lines are either perfectly horizontal or perfectly vertical. If we remember from yesterday, x equaling a number will be what type of line? Be a vertical line. One way to know is it tells you what axis it's going to cross. If it's x equals a number, it's going to cross the x-axis, which has to be a perfectly vertical line. Since the inequality is strictly greater than, it'll be a dotted line. Now here's the hard part that kids, oh no, it crashed on me. Hopefully it saved. Nope. Oh, yes it did. Sort of. So here's our dotted line. Now all we have to do is read it. This inequality literally says x is greater. Now again, knowing our coordinate system, x plus, x minus, y minus, x gets bigger in which direction? To the right, so we shade to the right. So shading, doesn't matter if I give you a special line, a regular line, all you have to do is read the problem. I know it's going to be tough for some of us. We have to read. A lot of us like to skip the instructions, but we have to read. Okie dokie?
Yes.
That's it. That's linear inequalities. It's just like graphing regular lines, except you have a little bit of extra reading to do and extra shading.